welcome everybody to this workshop. We are going to wait 1 or 2 more minutes and then we will get started covering mode 3 and mixed mode interlaminar fracture toughness. You can already, oh no, you cannot see my screen yet. Okay, we have a little bit more than 50 attendees already joining the workshop, so we will get started now. So today we are covering mode 3 and mixed mode. We have already covered general aspects of fracture toughness. We have covered mode 1 in a separate workshop, and we've covered mode 2. And I also have an overview here of previous workshops that we've had. First was on strength of composites. Just here you have the links of some of the latest ones. And now you see this part of the series on fracture toughness. And I will also include all the links here in case you want to look back at the previous workshops. So today it's mode 3 and mixed mode, interlaminar. We still have 2 more workshops that we will do over the next year or so. The first one being interlaminar fatigue, and then translaminar, both in tension and compression. And then we consider our series on fracture toughness to be completed as well. What happens after that is not decided yet. The objectives of these workshops are always the same. We want to raise awareness of difficulties, mainly experimental difficulties. What are the best ways to gauge these properties experimentally? We want to help the community to identify best practices and also hopefully to identify next steps in order to improve our best practices to get better experiments, get better data out of these experiments. Brief overview of the agenda, which was also included in the invite. After this brief introduction, I will present the paper that we shared alongside the invitation for the workshop. Then we will have our short presentations. I'll give you an overview of which ones we will have. Then we first have about 20 minutes for panel member discussions and questions. We'll have a short break of about 10 minutes, and then after that we will also open it up for questions from the audience. You can put that both in the Q&A, or you can raise your hand and then we'll try to go in order of appearance or in order of importance or popularity. At the end, we leave some time for conclusions, suggestions for next steps, and potentially also discuss topics for next workshop. We will definitely stop sharply at 5 o'clock. If we run out of discussions, maybe we stop a little bit sooner. We'll see how it goes. The 5-minute presentation that we have, unfortunately, we have one last-minute cancellation from James Radcliffe. He had a pre-flight test that he could not miss out, so he notified us a few days ago that he couldn't make it today. We do still have 4 presentations. Unfortunately, also the last one will be a recorded presentation because Jaime Viña had to attend a meeting that was imposed onto him and he could not be present there, unfortunately. Then a few ground rules. This is now the first time we do it in Teams instead of Zoom because we lost access to our Zoom license. The session is still being recorded and will be placed on YouTube afterwards, and you can also see all these recordings of the previous workshops on YouTube. The slides will also be shared afterwards. We have everybody who registered, we have their email address, and we'll send it out to all of these people. This typically takes about a week for everything to be uploaded, so expect this to take somewhere next week. You should probably receive it. During the discussions, you can already write questions in the Q&A, or you can raise hand at any time. We will only get into discussions after the presentations are over, though. The general attendees, they cannot use a microphone or a camera, but if really needed and you want to ask your question orally, we can give you the rights to open your microphone and your camera if needed. You can use chat for some general comments or saying hi to certain people, but the actual questions, please put them in the Q&A, then that way they're nicely separated out. And with that, the short briefing is over. I will now open the topic presentation, and then I will share my screen again. Can you confirm you can see that again?
Yep, all visible.
Yeah. Okay, good. So I will basically present the content of the short paper we have shared alongside the invitation, covering the main aspects of mode 3 and mixed mode interlaminar fracture toughness. Maybe first starting a little bit more generally about toughness of composites. I think most people here will know that toughness is the property that will control whether a crack can actually grow given certain loading conditions, or whether it will not be able to grow. In these workshops, we've often had a focus on trying to assess whether a certain property is a material parameter or not. If it is a material parameter, that means it's independent of the lab, the operator, the machine. It does not depend on the layup, and it should be size independent. And it's very much an open question whether this applies to toughness, because not depending on the layup is very doubtful for toughness. Not being size independent may also be doubtful, and it's very difficult to standardize some of these tests. So this is very much an open question in the specific case of toughness of composites, and maybe even more so in mode 3 and mixed mode. Starting off specifically with mode 3, this is probably the least commonly studied of all the different interlaminar fracture toughness properties we can study, but it doesn't mean it's not relevant. It does happen around bolt holes in certain impact loading scenarios, in real structures. So it is still important that we can study it, that we understand what's going on. But in general, it tends to be very difficult to achieve a pure mode 3. This is just not a single test is really able to fully reproduce only mode 3 without having some, for example, mode 2 attached to it. One of the most popular tests is the edge crack torsion test, which you see illustrated here. Essentially, you have on 3 corners, you support this panel, and then you push it down on the 4th corner, and the panel already has a pre-crack or a delamination along an entire edge of that panel. And this gets you something that is largely mode 3, not entirely, so there is some mixed mode present. And the biggest problem with this test is that it tends to be very sensitive to the boundary conditions, and it's very difficult to monitor them and get them set up to get you as close as possible to pure mode 3. So there have been other tests that have been developed, like the split cantilever beam. You can see this as a double cantilever beam, but then just loading it in the other orientation, and you can see that illustrated quite nicely on the image. Another approach is to use an angle ply laminate, apply a delamination along the both of the edges, and then simply put it in tension, and then you'll also get mode 3 dominated crack growth, and you can study how the delamination grows in that particular loading scenario. If we move to mixed mode bending, then the most common test is the MMB or mixed mode bending tests. This is also the only test today that we will cover that is standardized in ASTM D6671. You can see it illustrated here. It's essentially a double cantilever beam with a bit of a twist on it, which is a bit of a with a sort of end notch flexure type of loading. And by controlling the lever that you have here, moving it left or right, you can also change the mode mixity and study a wide range of mode 1 to mode 2 ratios. The data reduction methodology does require the elastic moduli and also an accurate crack length determination. And this works reasonably well when it's mode 1 dominated, but the more mode 2 you get, the more difficult that crack length determination tends to be. So there have been other alternatives developed, a lot of other data reduction schemes beyond what is mentioned in the standard. There are also other actual tests like the RCAN type tests, where depending on how you put the specimen or which angle you mount it in, you get either pure mode 1 on the left, pure mode 2 on the right, or mixed mode in the middle image. Another alternative is to use a symmetric specimen, but then load it asymmetrically in a double cantilever beam. So essentially one of these two forces would be larger than the other, and in that way you also introduce a mixed mode 1 and 2 combined together. If you look overall, you can see that these tests are some of the most challenging ones that you can execute on composites. It also tends to be rather difficult to extract the data. You need to know very well where the crack is, how long the delamination is, what the shape is, and it's very often not a straight delamination front. That's also why there are many different test methods available, and there's no settled agreement on what is now really a very good test. There's also some more philosophical questions, which we'll get into partially during the discussion, I think. There is a question whether mode 3 even exists for a 0-0 interface, or whether it will immediately just migrate. And can mode 3 even be distinguished from mode 2? Or do they just lead to the same fractographic observations? And with that, I will conclude the presentation. We will get into the presentations by our invited speakers, and we will start off with Emile Greenhalgh from Imperial College London. Emile?
Okay, great. Let me just share the screen. Okay, is that visible?
Very good.
Yeah, cool. Okay, well, thanks for this opportunity. I'm going to go through some fractographic observations related to mixed mode and mode 3 fracture and the associated process of delamination migration. So this is really, rather than going at this from the point of view of doing testing, we're focusing on trying to understand what's the fracture processes involved under those delamination conditions. So starting off with the mixed mode 1-2, if you look at the general stress state in that condition, you essentially have mode 1 tractions out of the plane of the laminate, and then these interlaminar shears that develop. And that results in an inclined crack at a particular angle, which is associated with that resolved stress. So from a fractographic point of view, what we see on the fracture surface are these features called shear cusps, and these are very characteristic. If you look at a mode 2 or a mode 1-2 delamination, these are essentially these angled cracks which have developed. And the important thing that comes out of this is that these cracks drive, under these low mixed mode conditions, drive upwards through the laminate, as shown here. So I've exaggerated the thickness of the interlaminar region to illustrate this cracking process. And then if you inspect these cusps and look at the angle at which the imprint of the cusp has developed, you can see that this angle actually relates to the mode mixity. So the higher the mode 2 component, the higher the inclination of these cusps. So this is observations that we've made from looking at fracture surfaces in mixed mode 1-2 in unidirectional laminates. But then when we look at multi-directional laminates, we start to see another process occurring. And what comes out of this is a fundamental rule that delaminations want to grow along the fibers. This is really a fundamental aspect of how delaminations grow in composites. And if you design your interface such that the upper ply under the loading conditions like I showed earlier is in the growth direction, so this is a UD for instance, then the crack will just grow along that interface. So this is a fracture surface of a mixed mode delamination specimen, and there's no migration processes. But if we try and force a crack to grow in a different direction to the fibers, this sort of situation, then what will then happen is we get migration occurring. And so the crack, initially starting at an interface, will migrate through the off-axis ply into a new interface. So this means that trying to measure the fracture toughness of a multi-directional interface can present problems. Because if you have this situation where the upper ply is in the growth direction, then you can characterize the toughness. But if it's not in the growth direction, you get migration and you no longer get a pure delamination surface. And so how this manifests is illustrated here. So this is some work that we did on an embedded delamination in a composite laminate under compression. It's a quasi-isotropic laminate. It's a 50mm diameter defect. And then this is showing you the damage width against applied strain. And the particular one that I want to focus on is the one at the 0.90 ply interface. So once we've done the test, we open that up. The delamination doesn't stay in the same interface as the original defect. It actually migrates through the layers. So this is zooming in on this area shown in red. This is the 0 ply. This is the edge of that PTFE insert. And then these are the next ply interfaces. So what happens is that crack jumps down through the layers because you're trying to force the crack to grow in a direction which is not in the direction of the fibers. And in order to propagate outward, then it has to jump, it has to migrate through the layers. And so this really starts to invalidate this concept of cracks being self-similar in their growth. Early work assumed that if you grew a delamination in a composite laminate, it would stay in the delamination original defect plane, and it doesn't. And this is all related to that migration process. So we tried to scrutinize what's actually going on here. So we started to rethink the definitions of mode 1 and mode 2 and mode 3. So from using a virtual crack closure type methodology, you can define a mode 2 in this type of instance, and then a mode 3, the tearing mode, as transverse to that. But because delaminations like to grow along the fibers, we defined a different, more local mode 2 and mode 3, where the mode 2 component, we've used small letters here for this, is along the fiber direction, and the mode 3 component is transverse to that. And this shows some nice correlation with the fracture morphologies that we see. So if we have a local mode 2 that dominates, then we see shear cusps which are orientated perpendicular to the fibers. These are the fiber tracks and these are the cusps. But if we start to introduce that local mode 3 component where we're trying to drive the crack in a different direction to the fibers, we start to see these cusps are twisted or rotated with respect to the fiber direction. And if you get to a mode 3 dominated condition, which is where migration occurs, so this is actually often a transition region within the material that it will start to develop these sorts of features, fractographic features, and then it will migrate into a new interface. Under those conditions, the cusps are parallel to the fibers. So this angle, as illustrated here, actually gives a measure of the local 2-3 ratio. So where we try to take this is, what is the growth angle that you can drive a delamination that causes it to migrate? So if it's along the fibers, it doesn't migrate. But if you start to deviate from that, what angle could you get to where it starts to migrate? So we developed a test called the width tapered end loaded split test, whereby we apply a point load to this diamond shaped specimen. And you can imagine as you apply a load here, as you move away from this point, you start to develop a higher mode 3 component. But of course, we defined the mode mixity locally using the expressions that I showed earlier. And then by scrutinizing the fracture surfaces and doing ultrasonic scans of this time of flight scans, we started to be able to identify where that delamination had migrated. So this is a graph showing you the local mode 2 and the local mode 3 across the width of this specimen. So if you look at a region Out here, for instance, here the local mode 2 is dominating. As you can see, the red line, and so we get cusps that are staying within the original defect plane. But as we move towards the left here, we start to find that the mode mixity now is pretty much equal the mode 2 and 3 components, and we start to see migration occurring. You can see the cusps are twisted with respect to the fiber direction. And that actually allowed us to come up with this particular material system. What is the critical conditions for migration to occur? So that was my sort of summary of what we've done from a fractographic perspective to try and understand mixed mode 2, 3 and the migration process that occurs. Okay, thanks.
Thank you, Emil. Now we move on to John Allen Pasco from TU Delft.
Yep, good afternoon, everyone. You're going to see some similar findings from our work, so nice connection there with what Emil showed. So I'm going to present briefly some work on planar delamination growth under out-of-plane load, and what it has to do with mode 3 will quickly, I think, become obvious. Just to very quickly motivate the work, we do a lot of testing in the lab on these kind of standardized or accepted specimens in the community, which are typically beam-like coupons, where we can treat the crack growth as essentially one-dimensional. But what we're actually trying to predict in reality is the behavior of large structures, which have quite different features. And in particular, the damage modes that you see in a large structure, like an aircraft, might be quite different because all kinds of things happen that you do not see in these beam-like specimens. For example, delamination in a large structure typically grows in a planar fashion, so it's a two-dimensional delamination growth. So we were trying to step one step closer towards understanding these more, let's say, realistic damage patterns. And so I had a PhD candidate, Venji, and the results I showed today are mainly from his work. He developed this planar delamination growth testing setup. So you have, let me see if I can activate laser pointer. Yeah, so we have a square specimen that's clamped with rubber between these two metal supports. And then we have out of plane an indenter with a rubber head pushing onto the bottom of the specimen, pushing it up out of plane. And then in the middle, we have a Teflon insert to initiate the delamination. And so the typical pattern that you see looks like this. So this is an ultrasonic C-scan image where the color represents the depth through the material. So we see we had an initial delamination here in the center, or initial Teflon inserts, and we see these two distinct delamination planes, because essentially, as Emil explained, immediately at the edge of the inserts, if the fibers are not aligned with the preferred delamination growth direction, the radial outward direction, the delamination immediately migrates until it finds a plane where the fibers are aligned. And if you have a bit more complex situation, then we get a picture like this. Here's a slightly different layup where we had actually a hole halfway through the laminate, but the same idea holds. So the delamination grows in the direction of the fibers where it can, and if it can't, and it immediately migrates until it finds fibers going in the right direction, it grows along those. And in fact, you then even get an additional migration a bit further out in this 45-degree direction. And so what you see is an area where kind of the delamination is happy to keep growing where it is. And you mainly see these fiber imprints, maybe some cusps. Then you see an area where you really see matrix cracking. So the delamination appears to be trying to migrate, but it's then being blocked by the surrounding fibers until it eventually can break through. And then over here, there's immediately migrates and then continues smoothly in that plane. And then if you do a VCCT analysis, this is still based on the global analysis, I think. At the insert front, and this was a case where there was a 0-0 fiber interface, then you see there's a region where you find predominantly mode 2, and there's a region where you find predominantly mode 3. And the mode 3 region is, as you expect, where the delamination immediately migrates, whereas in the mode 2 area, it remains in the plane. And then you have in between this mixed mode area where we get this additional matrix cracking. And then also, if you notice, you see kind of that the growth is a little bit slower in those directions, right? So that matrix cracking may be somewhat toughening the material or the specimen. We can argue a bit about material properties and so on. Here, just again illustrating here. So if you have this mode 2 condition, then the crack migration is blocked by the upper fibers, whereas in mode 3, the crack can continue growing in between the fibers and migrate to the next plane. And this is what it looks like then if you open up the fracture surface and look from the top. So we have over here the migration boundary, here an area where there's the pure mode 2 growth, here area of pure mode 2 growth as well, but then in 90-degree direction. And in between we have this region where we see some matrix cracking, but not full-blown delamination yet. So not full-blown migration yet. So the delamination is trying to migrate, but it's still being blocked. It can't break all the way through, but it is kind of diving into that adjacent ply. So in conclusion, what we see, if the fibers are not aligned with the delamination growth direction, or the preferential growth direction, we immediately get migration to the blocking fibers, so where the fibers are aligned in the growth direction. We see a pure mode 3 region pre-migration, so that explains why we immediately get this migration happening. And there's a mixed mode 2-3 region where we see this matrix cracking. And we could imagine that this matrix cracking, of course, also takes energy and is therefore slowing down the delamination growth. And so we have higher delamination resistance. So that's very briefly the findings. You'll get the slides if you want to have a look at some additional information. You can look up these references. We also just released with the D-Standard project a large data set, not of mode 3 testing, unfortunately, but there's a lot of mode 2 quasi-static and fatigue testing in there, also mode 1. So if you're interested in that to play around with or validate your models on, then feel free to follow that link. And then, the questions and discussions will happen later on. Thank you very much.
Thank you, John Allen. Then we move to Andreas Brunner from EMPA.
Okay, also welcome from my side. I hope you can see my slides. Is that correct?
Not yet.
Not yet. Oh. I think I tried to share my. Oh, do I have to try again? Maybe.
That's better, and I'm in full screen.
No, just oops. So, yeah.
Yeah.
Is it okay?
Yeah.
Okay. So, thank you very much for giving me also the opportunity to present here in this workshop. And in my presentation, I would like to raise two aspects for discussion. The first is, as the previous two speakers have clearly said, these mixed mode and mode 3 tests are quite complex and difficult to do. So the question is, do we really have to test these modes? And on the other hand, if we finally feel we have to, what is the best approach to do that? Okay, this has all been explained before. So there's this ASTM mixed mode bending test, the similar setup that Yentl showed before. There is an alternative, which is called a fixed ratio mixed mode 1-2 test. And this is not standardized, but within ESIS-TC4 we're working on standardization of that. The big advantage of this test is that the mode mixity is clear. There's no argument that this test yields a mode 1 to mode 2 ratio of 4:3, whereas in other tests, sometimes it's not quite clear what the effective mode ratio is. Then, of course, there are many different mixed mode tests, all kinds, different mixes of between mode 1-2, 2-3, 1-2-3, etc. And a large range of specimens that have been proposed. So, for example, there is this modified compact tension, or this triple pant leg specimen, the double notch split cantilever beam, then the width tapered ELS test, or then the shear torsion bending, and of course also the argon fixture can be used for that. Now for quasi-static mode 3, it has already been said as well that there's no standard. There was an ASTM round robin performed in the early 1990s, which used the 4-point edge crack torsion test, but this never led to standardization, and no one has picked up that as far as I know. Okay, there was the split cantilever beam, or there's also a modified version of that. The references are given on the last slides then, where you can look it up. Then this is the edge crack torsion, the 4-point version in the schematic here, and a photograph of the 6-point version that has also been developed. And the point I would like to note here is that quite a few of these tests use more or less plate type specimens, but as it has already been said, it's typically additional mode mixity, mostly mode 2 with mode 3. There is an edge ring crack torsion test. The one that is shown here is called longitudinal half-fixed beam, but then the edge ring crack torsion test is shown here. And according to the authors, they say that this is a pure or essentially pure mode 3. However, the disadvantage of that test is it's unstable. So you can determine initiation values of mode 3 fracture toughness, but not any propagation, which of course would be required if you wanted to apply these data in structural design, because you have to understand how the delamination will grow and propagate. So now, looking at that from the other side, if we, for example, have a set of data from quasi-static tests, and this is an example taken from the PhD thesis of Michael Zwickowicz at Leuven in the early 1990s. He did mode 1, mode 2, and a range of mixed mode tests, and then he got these empirical failure envelopes that are shown here. And Kevin O'Brien in the paper noted that the delamination propagation in fiber-reinforced polymer structures basically require understanding mixed mode, typically mixed mode 1, 2. And on the other hand, from round robins and tests, we know that the repeatability, which is basically the data from one lab in terms of standard deviation, are roughly something like plus minus 10%. For mode 2 and mixed mode, it can be a little bit higher. And the reproducibility, if you look at round robin tests performed at several labs, then we end up with somewhere between 15 to 25%. Interestingly, if you try to estimate what the kind of the maximum scatter is that you can expect from the required measurement resolution in the standards, you get something like plus minus 5%. So there are external factors that produce a lot of scatter, and in this reference 18, I discussed some of that. If you're interested in more details. Now, the question I really want to raise is, do we really need the mixed mode 1-2 data for safe structural design? If you look at the graph, you can see that, you start at the kind of value for the mode 1 at around 300 or slightly below, and then the kind of this failure envelope goes up quite steeply, and so in principle, this could suggest that if you simply take the mode 1 and apply sufficient safety factor, then you could probably do with that, and you wouldn't need any mixed mode test for the design. Of course, the question then is, what would be the safe design limit in terms of the standard deviation? Now, it has already been mentioned by John Allen that, of course, in real structures, for example, thin shells, which represent a lot of the structures that we have, will yield two-dimensional propagation, which is, of course, different from what we get in the beam specimens. This is taken from the PhD thesis of Ida Camiselle Molares at EPFL. This is a quasi-static mode 1 test on a plate, which had a circular starter crack at the center, and then was loaded in mode 1. And there were quite some phenomena that you wouldn't expect, or you would not be able to see in the beam-like specimen. So there's kind of a a stiffening, softening behavior, and there's a transition point somewhere. And the same methodology and this was done at TU Delft, has been applied to a mode 2 test or a mixed mode 1-2. And this is the test setup and the schematic of it. And of course, you could probably think of tests, and John Allen has shown example where you could also involve mode 3 in these tests. But of course, these are more complex specimens and more complex test setups than what you need for the standard beam specimens. Now, as a summary in the outlook, I mean, if you take these failure envelopes from quasi-static mode 1 or mode 2 or mixed mode tests, we do not get, let's say, what I would call useful prediction of the emanation propagation behavior in real FRP structures. This is discussed in two references, for example. If you run the tests on something like square plates, as shown in the previous slides, then we possibly could get better predictions, but of course it's much higher test effort and of course also higher test costs. And the question is it worthwhile? There are two things that kind of play a major role, and has already been mentioned before as well. So fiber bridging plays a role, and then that kind of highlights the importance of the fiber orientation or the laminate layup. And but as I also tried to point out, there are specific effects that you will not see in kind of 1D beam specimens, but you need really 2D specimens like this stiffening, softening behavior in the mode 1 test. Now the question is, if we kind of reduce the test effort to mode 1 from beam specimens, which are easy to do with a safety margin that would have to be specified in design codes, for example, of course we run the risk that it could be too conservative, which means we will give away a kind of some of the potential that the material has. But then on the other hand, and this has not been discussed in much detail yet, typical fiber-reinforced structures, you don't have a single delamination. You have multiple delaminations in different planes, and depending on how many there are, their shape, size, etc., you will run into interactions between these. And then the quantification of the toughness becomes extremely difficult. And then, of course, also the question is, are quasi-static tests sufficient? Because the real service loads are typically variable fatigue loads, and both with respect to amplitudes and frequency, including also variable environmental exposure, varying temperature, humidity, etc. And that also will have a big effect. Of course, I think this is a topic for later workshops, but I thought it was worthwhile to point that out. So I have to acknowledge a few people for information that I drew on, and these are the references, and thank you for your attention.
Thank you, Andreas. So now we first start off with about 20 minutes of discussions between the panel members before we also open it up more broadly. So I'll ask all the panel members and the presenters.
What about James' presentation?
Yeah, sorry. My bad. We still have one more presentation, which will be a video recording, which is not ideal, we understand, but we thought it was definitely useful to have this, so I will.
My name is Jaime Viña, and I am professor at the University of Oviedo. I've spent my entire career doing research in the field of composite materials, mainly focused in the interlaminar fracture. In this short presentation, I'd like to talk about our work on mode 3 fracture testing. The title of this presentation is a novel methodology for mode 3 testing of laminated composite materials. Here we present some of our papers in the field of fracture composite in mode 1 and mode 2, both static and dynamic And here we have the same static and dynamic, but in mixed mode 1, 2. And at this point, we decide to explore mode 3 testing. But when we review the literature, we found that the usual test was not very satisfactory for us. Why? Because the static test in mode 3 was our first objective, but we want to carry out testing, dynamic test in mode 3 also. Then we found in our laboratory this machine with an axial capacity of 60 kilonewtons and a torque possibility of 250 newtons meter. Then we designed an easy device with this part is fixed and this part is we can move. It can move with the application of torque, and we put here the specimen. In order to check the purity of the mode 3, then we use digital image correlation system, and we take measurements from the line of the insert to 0.5 millimeters, 1.5 and 2.5 millimeters. Here we can observe the specimen, the test machine, the test with the DIC system, and the axis, coordinate axis X, Y, and Z. In this slide, we present the results of the mode 1, mode 2, and mode 3 that we obtained in a point at a distance of 1 millimeter from the front of the insert. Here is the same, but at a distance of 26 millimeters. And here we can compare the results at 1 millimeter and 26 millimeters. We can with the red color, with the orange color is mode 3, and blue color is mode 2. Finally, we present the fractography, a little fractography analysis. We test two different materials with the same fiber, AX4, and different matrices. In this case, is the matrix 8552, and we can observe an important vertical displacement of the fibers in the direction of the torque. Also, we can see the broken fibers, typical, because we have an important bending in the fiber. And also in this slide, in this photo, we can observe a typical morphology that we find in these materials, in this kind of tests. They are the caps. The caps, this is these lines, and they have an angle of 45 degrees from the direction of the longitudinal fibers. Also, for ease of interpretation, the stress state generated at the point in this fracture region have been generated in this figure for a reference system XY, where the x-axis is located along here, along the longitudinal direction of the specimen. This stress state is dominated by tangential you can observe here the tangential stresses in the direction of this reference axis. The main tensile stress generated in the specimen, obtained by means of Mohr cycle, are likewise represented in the figure. The orientation of these stresses is shown, as well as the plane in which they operate, which basically coincides with the observing fracture planes. More or less, with the other material, with this matrix, we observe also the caps, but appear a new morphology that we give the name of saw teeth, more or less. And these are the papers in which we developed and tested this methodology. And finally, thanks for your attention. And if you'd like to comment anything, please email to this direction. Thank you very much. Bye-bye.
Okay. I'm sorry. I think for some people that didn't work quite well. For others, it was flawless. So I'm not sure what happened there. I hope at least most of you have been able to follow this. Now we will actually get into what I was saying earlier, to discussions among the panel members first, and then we'll also be waiting for questions from the audience and take those afterwards. So anybody who wants to kick off the panel member discussion?
Well, let me kick off a question for Emil. Very interesting presentation you gave there. I'm very interested about the angle of these hackles. And is there a sort of a critical limit of how much angle you can get before it migrates? Does that depend on the material, or what controls that migration behavior, and how much potentially off-axis hackles can you get?
It is. I mean, I think there's still a lot of questions to answer on this, because certainly I've seen when we try to do coupons where we try to grow cracks at an angle, we see this migration process occurring. So the samples that I showed you, the width-tapered end-loaded split specimens, I think the angle was relatively small at which that migration process then ensued, and we didn't get those cusps parallel to the fibers. But then I've looked at structures and I've seen cusps, as I showed the image of, which are almost parallel to the fibers. So I think there is a bit of a disconnect of what you can generate in a coupon and then how that can manifest in a structure. And I think there's still a need for some sort of test to characterize that. Certainly the materials that we were doing, the angle doesn't need to be very much to get that migration process to occur. Order of 10 or 15 degrees, I think, off the fiber direction. But I think there's still a lot to be done here to understand, what's actually going on. And I think wasn't there some work at Bristol done by Pernice on the sort of migration process in more detail?
Yes, I think that was a bit more. I don't think that was really related to mode 3 from what I recall. It was mainly the sort of looking at the mode 2.
Yeah, but I think it's all interrelated. I think this is why this idea of the local mode 2-3 mixity, which is aligned with the fibers, becomes important, because essentially that mode 3, that local mode 3, is associated with trying to drive the fibers, drive the crack across the fibers, and which leads to migration ensuing. But then if you move to woven materials and materials that aren't able to have interlaminar fracture so distinctly, then I think, again, it becomes even more complex under those conditions.
I'm just wondering whether it's really the angle with respect to the fibers that's important, rather than whether you define it as mode 2 or mode 3. Perhaps that's what you were alluding to when you're talking about the local.
Exactly, yeah. We've defined this local mode 2 and 3 with respect to the fiber direction. And it just seems to be that it's a fundamental thing that delaminations want to grow along the fibers. That seems to be something that I think that needs to be implanted into models, predicted models for damage growth, because if you do that, I think you'll have better predictions. But how you turn that into a cohesive law or something like that, I'm not quite sure how you do that. Thanks.
More questions from panel members?
Yes.
Okay.
Federico?
Can you hear me?
Yes.
Yeah.
You cannot see me?
No, unfortunately not.
Just to avoid to help me with my hands to what I want to say. So, well, first of all, thank you very much to all presenters. And I don't have a particular question for any of them. It's just a generic comment that is a reflection on the problem we are now today discussing. We said at the beginning, we the organizers, that there will be 3 requirements to be a material parameter. My answer is that the matter we are dealing with does not satisfy any of the 3. So, and I'm going to try to explain this and to finally to reach a conclusion. When brilliant people started fracture mechanics theory, they did not have in mind the material we have. And mode 1, 2, and 3 were extremely relevant for isotropic and homogeneous material. Typically, we pay attention to the fact that composites are not isotropic, but in the particular case of analyzing fracture, anything related with the final state, the final the strength, toughness, is not associated too much to the non-isotropic character of the material, but to the non-homogeneous character of the material, in my opinion. So it means that talking about composites or about interlaminar properties, as I understand that the property, let's call property, we are measuring is associated with the mechanism of damage. And the mechanism of damage is at a micromechanical level. So when talking about interlaminar property, we have to look to the micromechanical mechanism of damage. And this, for me, explains everything. So, for instance, I absolutely agree with the representation that Emil has in the, I think in the 4th, and he has explained in the 4th screen, distinguishing in between G2, G3, and GII and GIII. Absolutely agree. But if we accept this, then we are assigning mode 2, mode 3 to something that is not connected with the origin of fracture mechanics. Yeah. So even with the same specimen, but different orientation of the fiber, we could have either a GII or G2 value or GIII or G3 value. So with this, let's say, reflection, my impression is that what we got always, we will get always is a, let's say, in situ value. So it's applicable. We get this value from one particular test, one particular specimen. And this value for people that design aircraft, for instance, is useful if they know that the situation of stresses, orientation of the fiber, etc., is the same in their application than in the test that we have performed. Which means that probably the situation is that typically the smallest value is the one taken for designers to make a prediction of the behavior of the composites. So this, going to the initial comment, I think that these are not material parameters, are parameters that we can use for designing if we can connect the test with the application. Sorry, I've been too long in my explanation.
Emil, do you want to perhaps respond to that?
Yeah, I very much agree that the fact that the conventional design, the conventional definition of mode 1, mode 2, 3, and 3 were all related to isotropic materials. And I mean, early in my career, I got very frustrated that everyone was doing fracture toughness tests on unidirectional laminates, but real structures are very rarely unidirectional laminates, they're multidirectional. And certainly when we were characterizing the fracture toughness of multidirectional laminates, multidirectional interfaces, the toughness was different because there are added mechanisms that occur that don't manifest in unidirectional laminates. So I think actually using unidirectional is conservative, but my feeling on the migration process is that we were finding that the migration process really had a big impact on the damage growth. And if you could encourage the migration process to occur, it would actually lead to a very slow damage growth, because you were trying to force the delamination to grow in a direction that it couldn't do, so it was migrating, and that was causing a very tortuous crack path, and so the damage growth was very limited. Can I share the slide again to sort of illustrate this?
Of course. Yes.
Just go back to this slide. Share screen. Okay, so into presentation mode. So it's this graph here, which is showing the damage width against applied strain on the laminate. In the case of the ±45 interface, so this is between the fifth and sixth plies, basically would jump into the 90 ply and then shoot along, and this is why the damage growth was quite rapid. But in the 090 ply interface, this was the process that occurred. So all this migration process was really inhibiting the damage growth, the transverse damage growth. And we were getting up to 9,000, 8,000, 9,000 microstrain before final failure occurred. So my feeling is that we should be exploiting the migration process to improve the damage tolerance of structures. And I think having modeling techniques that can capture the migration process and be able to model the sort of damage that I've got on the screen here would give us a route to having much tougher, more damage tolerant structures.
Sorry, Emil, I don't quite understand this graph. Is that showing the delamination width in different specimens or in different interfaces of the same specimen?
They were the same configuration, the sort of plus minus 0.90 stacking sequence.
Different insert position.
Different insert depths, yeah. So the 0.90 was between the third and fourth ply, right. And then the plus minus was between the fifth and sixth ply, but everything else was identical, the defect size, the loading conditions and everything. And it was just when the delamination is between the fifth and sixth ply, it jumps up an interface into the interface where the 90 ply is the upper ply interface, and that in that instance the 90 is in the direction the delamination wants to grow, which is transverse. So this is why it rapidly grows across, and you only get up to about 6,000 microstrain. But in the 090, it jumps up through the layers, the upper plies, and never gets into an interface where the 90 is dictating the growth. So leading to this very convoluted process, which leads to a very sluggish damage growth. But everything else, the samples were identical. And in fact, there are two tests here. And you can see it's very repeatable as well, which gave me a lot of confidence that this wasn't just some experimental error. This was something that was inherent mechanism in the material.
I think that's very interesting. I think it just shows how important these transverse cracks are, because in allowing this migration to occur, you change the amount of energy available, and therefore can change the degree to which it propagates, as you show very nicely there.
Yeah.
And you see so sort of switching to another thing, if you use thin plies, then you tend to suppress this matrix cracking, and then that may actually change migration and therefore the delamination behavior. I don't know whether you ever looked at the sort of thing with thin plies.
No, I would have liked to, but the problem with delamination is that we've been working on it so long, it's very difficult to get funding to look at it, basically.
Can I comment on that, please?
Yeah.
Yeah.
I think there are two aspects. I agree with Emil that making the delamination path more complex, tortuous, whatever, is of course beneficial for improving structural integrity or damage behavior. However, with unidirectional, we have now the big discussions while we're in developing these cyclic fatigue tests, where mode 1, due to fiber breaching, may not really be a conservative value anymore. So that is one aspect. On the other hand, I've seen a few papers where people put sacrificial defects in. I think there was a paper by John Batsis from EPFL and a few others. And that, of course, is also a concept that could help. Of course, it would have to be balanced, improving toughness versus reducing strength or elastic modulus and all that. But this has not been explored that much. Or do you see that as a viable option also?
Yeah, I think anything that deviates the crack path would be potentially a way of improving the toughness and the resistance to crack growth.
I would like to ask a question to Andreas. You had this slide where you showed, I think this is an outcome from this round robin, where you show a plot going from mode 1 to mode 2 and then everything in between. But surprisingly, this is not a parabolic shape, because as soon as you add a little bit of mode, I think it's mode 2 to mode 1, it actually increases the toughness beyond the original mode 1 toughness. Is that a real thing, or is it just an artifact of which line was fitted through?
That is debatable. Actually, it's not data from a round robin. It's the PhD thesis of Michael Zwickowicz, which was performed in the early 1990s at Montanuniversität Leuven. And Michael then moved to NASA Langley, and I think he stayed in the US. I'm not sure where he is now, or maybe he has come back to Europe. I lost touch with him. Last time I met him was back in Langley, but many years ago. Of course, this is single test, so it's one person doing it. So all the scatter is basically repeatability. So it's one operator, one test machine, he did it on different types of materials. And the fitting line is an empirical thing. So in that sense, whether this represents the true behavior is really debatable. But I thought it was a nice illustration. I mainly used it because I could argue that maybe a mode 1 criterion would be sufficient, rather than having to consider all the other modes or mode combinations. But then again, the main point that I want to make also is, we have typically 10 to 20% scatter, either repeatability or reproducibility. And it is very difficult to distinguish, for example, then between different approaches for toughening, if we have such a large scatter band for each test or type of test. And that may make it difficult to decide what are the best approaches then to improve toughness, really.
Yeah.
Did that answer your question?
Yeah, absolutely.
So it looks to me like those lower three values are all got much the same G1 value. And the real thing you're saying is that a bit of G2 doesn't make much difference. But clearly, if you compare the G1C with G2C, there's a factor of 3. So in that case, for a pure mode 2 case, you use G1C, then you'd be very conservative. And the G2C, the G2 is pretty important in many cases, whether it's impact, whether it's ply drops. So I think perhaps that would be too conservative. I'd be interested in what other people think.
I feel it would be. It would be too conservative. You would give away a lot of the potential of the material by using it. But maybe other people can comment on that better than I do.
I guess some people in industry would take that perspective. It saves them a lot of testing. It is conservative, but they usually don't mind that too much. But us academics here, we would mind that quite a bit, because indeed you leave a lot of performance on the table that you're not really exploring. So yeah.
But I think it could be impacted on, if you took that approach, the mechanisms for mode 1 and mode 2 are quite different. So mode 2 is very dominated by the fiber matrix interface. So if you introduce moisture or temperature, you actually find the mode 1 toughness increases because it encourages fiber bridging. But if you do that for mode 2, high temperature or high moisture really pushes down the mode 2 fracture toughness. So you could end up there actually becoming non-conservative in terms of using pure mode 1 fracture toughness as your measure of material performance.
Yeah, very, very good point indeed. I actually maybe want to mix it up and ask John Allen a question, which is a bit sort of in preparation for the next workshop that we'll do on interlaminar fatigue. We've talked a lot about the crack migration or delamination migration, and I know you've also done this test in fatigue. Do you see any differences in migration behavior in static loading versus fatigue? I would guess not, but I don't know.
No, so in this test, not. I think was pretty much the same thing. So immediately migration and then growth. Although I'd have to check whether we had a pre-cracking, quasi-static pre-cracking phase, because then of course you immediately create that migration in any case. What we have seen, we've also been doing some testing in a different project, which I didn't show today in the D-standard project, where we looked at different fiber orientations in the more classical ELS and DCB tests. So we had a 0, 0, 0, 45, and 0, 90. And there we did see a difference. So what you saw in quasi-static testing is you get an oscillatory migration, or type of migration. It's a bit complex what we call it in some of the cases, but basically the crack front is going up and down between the two interfaces on either side of the angled ply. Whereas if you do it in fatigue, you get a single migration and then it stays there. And if you look at the fracture surface, you do see these kind of shear cracking into the migration. So it looks like it's continuously trying to go back down. But then in quasi-static it can, but in fatigue somehow it can't.
Yeah, okay, so there are some nuances that can be different.
Yeah, for sure.
I can also add, I mean, at Thomas Keller's group at EPFL, Aida Tomaselli Molaris, she did not only quasi-static tests, but also fatigue tests, cyclic fatigue. So there is experience, so there are data available from these plate tests, mode 1, and I think mode no, I think she did only mode 1, but she did also in fatigue. And if I remember correctly, there was not that much different. There are two major effects, and one is fiber layup or type of interface in that sense with respect to the reinforcement. And Hong Che-Wan, second PhD, he investigated the effect of the initial delamination, the starter delamination, and he used different shapes and sizes, and that also seemed to have some effect on the propagation. So I think of course these 2D delaminations are a very complex type of test to run, and there are many factors that have an effect. And you may remember if you see the photograph, of course when you start loading, you may get significant deformations in the plate, so more like a saddle shape type of thing. So it's not planar anymore, and it's not a single bending type of thing. That makes it very complex. And of course, then the question is which type of mode you really have at the crack tip, things like that.
Yeah. Okay.
Ask
Maybe one more
John
question from the panel members, and then we'll go into a short break, so we also have ample time for the attendees to ask us questions. Go ahead, Michael.
Yeah, so you showed a picture where you were talking about delamination to the 0, 0 interface, and you're showing mode 2 and mode 3 contributions. But I mean, you don't usually get delamination at a 0, 0 interface at all. And if you did, surely it couldn't be mode 3 because it would migrate, wouldn't it?
Yeah, exactly. So that's exactly what happens. So the delamination location is artificial because you put a Teflon insert at the midplane. And so we have a 0, 0 midplane with an artificial insert in there. then we're loading it out of plane. So in the one direction, so radially away where that's aligned with the 0-degree fibers, it grows in that stays in that interface. And at 90 degrees to that, it's immediately migrating one ply up where it hits a 90-degree ply, and then it runs along the 90-degree fibers.
So I guess that's consistent with what Emil was talking
exactly,
about.
Exactly, yeah. It's 100% consistent with that.
So in one direction it's mode 2, in another direction it migrates. And is there a critical area where the mode 2 stops and migrates? Is it just...
Yeah, so that's what we see. I can quickly go back in the slides. Right, so we see, then if I share the screen again. Right, so we see this area. So we have the insert is in this plane. We see that in this direction, the fibers are exactly aligned with the lamination growth migration, so radially out from the center point. So there it stays in the plane. So that would be mode 2, yeah, exactly. So then on this area, you would calculate, if you do it with VCCT, a mode 3 component. So there it immediately migrates, and then probably this is then again local mode 2, let's say. And then you see this kind of purple shaded area in between. That's an area where if you look on the fiber, on the fracture surface, you see a lot of matrix cracks. So it seems to be trying to deflect out of the interface it's in, but it can't quite break all the way through. It is being trapped. And then you see that eventually, if you get far enough out, then it manages to find its way through up to the 45-degree ply, because this was a quasi-isotropic layup in the end. So it's basically migrating up 2 plies and then continuing here in this region in the 45-degree ply, or below the 45-degree ply. So you have these, and so if you, and I think the interpretation of this calculation is debatable, right? But so this is the calculation around the border of the Teflon inserts before anything has happened. Purely global modes according to VCCT. So we can have a long discussion about how we should interpret this exactly, right? But if you do that, then you see there's this mode 2 region, there's a mode 3 region, and then there's a mixed mode region. And of course, in this mode 3 region, it's immediately migrating, and then, yeah, is it still mode 3? What exactly should it be, right? You do not have the situation that's being analyzed here anymore for sure. So you'd have to reanalyze what exactly is going on there. But yeah, that's indeed what seems to be going on.
Okay. I would propose that we take a 10-minute break, and then right after the break, when we resume at 25 past the hour, we will get into attendee questions. If you already have any questions, you can either already put them in the chat, or you can raise your hand if you want to explain it orally, if it's a bit more of a complex or a longer question, and doing it orally is probably easier. We will return in 10 minutes from now. See you then.
We don't seem to have any questions. So if there are any questions, please put them into the Q&A.
Yes.
Johan?
I thought Robin Olsen was going to ask a question. And I also saw at some point Giuliano Allegri was raising his hand during the panel member discussions. Yeah, okay, so there. So maybe the first one is sort of addressed to Andreas from Robin Olsen. I think you should also be able to read this yourself. He disagrees on just using mode 1 data with a safety factor, leading overly conservative designs. I think everybody can read this on his own. Do you want to respond to this, Andreas?
Yes. I mean, the main reason I brought it up is just to stimulate discussion. I mean, as I hopefully managed to point out, I mean, it's a question, of course, how much you want to be on the safe side or how much risk you can take in designs. And I mean, I was trying to balance this kind of regarding the type of tests. So mode 1 tests are simple, straightforward, don't need much material. Whereas a mixed mode test is already more complex, even if you use the MMB, etc. So I think it's, and I feel also, and that I also try to point that out, independent of which test we use, we may have to keep an eye on the scatter. And the intrinsic scatter, which comes from measurement resolution, tends to be fairly low, a few percent. But the round robins indicate 10 to 20, 25% of scatter. And I think we may also have to think about which test has the potential of reducing this to a reasonable, somewhere probably between 5 and 10%. But as I said, I mean, obviously I'm not really into the design of structures. And I mean, Robin Olsen is probably much more qualified to discuss that than I am. But I just thought it would be worthwhile to think about that, comparing the difficulties of the test and the effort you have to do. I hope this helps, Robin. Else you can comment again.
Yeah. And then there's a second question from Robin as well, which aligns with what Emil was talking about with the GIII and GII definitions. Do you want to respond to this, Emil?
Where are you seeing these questions?
In the Q&A. You don't see them, Michael?
Oh, yeah, they've come. They were blank. Okay, I just refreshed it. Thank you. Sorry.
Yeah.
Carry on.
Yeah, I'm just trying to incorrect define mode to sliding along fives. I mean, we were just trying, in terms of these local 2 and 3, it was very much driven by the fractography that when you looked at a local mode 2, you could have the fibers at an angle to the starter crack, I think as some of the image I showed. But actually, if it's growing along those fibers, then locally it forms these cusps that we see in a pure mode 2 test in unidirectional materials. But then, so that's really what was driven. Our kind of drive for developing the width taper test and trying to understand the migration process was all driven by the fractographic observations. And I think that's why we came up with this local mode 2 and 3. But I think there's still a lot to be done there. In some instances, you see migration occurring immediately. Other times you see multiple cracks and then it delaminates. I think this is the Pernice book I was talking about. And I also think what James Reeder has done similar type of work. So I think there's still a lot to be done in trying to capture that process and then actually put it into models as well. How would you use a cohesive zone method to actually define a preferable crack growth direction? I think that's something that needs to be.
I've given Robin the permission to speak and to use his camera so he can respond live.
Okay.
Cool. Hello, Robin.
Hello, long time ago. Yes. Yeah, I mean, I'm sort of a little bit annoyed by this thinking of, that a delamination along the fibers is mode 2 and transfers to the fibers is mode 3. I mean, it really is about how the crack surfaces slide with respect to the crack front. And I imagine that you are right that in practice, probably very quickly you get into migration, but it's not just about how the fibers are oriented. I would think that in many situations you can have a mode 3 as well as a mode 2. But, and I mean, the other problem we have is that we are so focused on these unidirectional specimens and unidirectional interfaces, which in fact are completely unrepresentative of the real cases where we get delaminations. You will never get, almost never get a delamination in a unidirectional specimen. And in impact, it always happens when the plies are actually of different orientation. And then you're right that it's sort of very important how the fibers link the crack growth. Once you have got the migration, but yeah, I think try to we talked about fracture mode. And the other thing, I just in my first question up there, I want to point out that, I mean, it's really a big difference in mode 1 to mode 2 ratio for different systems. And if you don't consider that, you will make a very poor design. What we have done so far is mainly brittle and semi-brittle materials. But if you look at, for example, PEAK, their G2C is about the same as G1C. So you really need the mode, at least a shear test, mode 2 test, to distinguish between mode 1 and mode 2 toughness. Ideally, we would like to have a mode 3 test, but for the moment, they are more or less useless, the tests we have. So I think we have to continue to work to find a good mode 3 test. I mean, initial studies, initial data indicate that G through C and G2C are pretty similar, and also morphology. If you look at that, people who have looked at the morphology with shear hackles and stuff like that see similarities in G2, mode 2 and mode 3 tests. So
no, they're different. They look pretty different.
But they involve hackles in both cases.
Well, they're vol cusps, but
yeah, cusps, exactly.
I think I showed the picture that showed when you have a mode 2, you get the very classic cusps tilted, aligned perpendicular to the fibers. With mode 3, you get these really long strips, almost like ribbons, which I think are the start of the migration process. And on fracture surfaces, I've not seen vast expanses of mode 3 fracture. This local mode 3 fracture, these cusps aligned with the fibers, that tends to be a transition region that ultimately turns into a migration.
That's
so
very
I think
possible, yeah.
I really struggle to think of an instance where I've seen a structure where you could say the mode 3 was larger than a few square millimeters or something. So I'm not sure that mode 3 is something that you can get in a steady state that you'd be able to demonstrate a toughness associated with it.
Yentl?
Federico, go ahead.
Yeah, I would like to say something about this topic. Look, Robin, I would have no problem in maintaining the classical definition of mode 2, as you said, as sliding transverse to the crack front, and mode 3 as growth along the crack front. I could accept this. The problem is what we put on the other side of the equation. In fracture mechanics, you have something that depends on the external loading compared with something which is assumed to be a property of the material. Now, depending on how the fiber arrive to the surface, you will have different values of your, let's say, G2C and G3C. The idea of putting the two modes 2 and 3 associated with the direction of the fiber is to maintain, to explore the possibility to have always on the right hand side of your fracture mechanic equation a representative value. And for this reason, I think that 2 and 3 do not have, in our case, the same meaning than in the origin of classical mechanics.
Yes, I agree. I think it's basically we're talking about the classical mechanics doesn't really apply because that's based on isotropic materials, I think, as Emil really explained. And in the composites, it tends to follow the fiber direction. And if it's transverse to fiber, it doesn't propagate, it just migrates. So we've got a fundamental issue that the composites behave differently from the classical isotropic case. Isn't that what it's about?
Sure, but I mean, there are cases where actually the laminations grow in a direction which is not exactly along the fibers. For example, we did at FFA, Aeronautical Research Institute, many years ago. We did tests in specimen where we used ±5 degrees to suppress fiber bridging. It worked fairly well. And I mean, you could see growth, which wasn't along the fibers. It was in the it was in the 0 direction already, although the fibers were in the 5-degree direction. And I think you can probably, I mean, Emil has looked at that. You can probably extend that a bit further when the fibers maybe to 10, 15, possibly 20 degrees. You can still have a growth in the original, let's say, 0-degree direction, although the fibers are not in that direction. But I mean, basically there is a competition between delamination growth, which happens in the sort of original crack plane, and migration. And of course, you cannot use delamination models with fracture mechanics and cohesive surfaces and all that for something which actually involves a growth which is intralaminar, crack growth through the plies. So I think you need models which can account for both and can tell you if you get migration or delamination growth.
Okay, I would propose we move to the next question. I see that there are 3 questions also in the chat. Please, for the next questions, try to put them in the Q&A. That's a little bit easier. We'll first do one in the Q&A and then we'll move to the ones in the chat. So, question from Helena Delmot is about dynamic loads and strain rate effects. Does anybody have any response with respect to the effect of strain rates?
So let me just make a quick comment. There's a couple of really good review papers in Composites Part A from Michael May about high rate delamination testing, and the conclusion is it's very difficult, and there's a lot of variability in the testing data, and rather variable results that have been found. So the reports have been an increase in G2C at high strain rates, but other results are not necessarily always consistent with that.
Can I also comment on that?
Yeah.
Please.
I mean, there is literature on, I think there are 2 papers by the Japanese, Masaki Hocho and co-authors. One deals with mode 1, the other with mode 2, dependence on strain rate. And it looks like that these effects tend to be fairly small. I mean, probably on the order of 10 to 20%. However, the problem is that not the whole range of strain rates was covered with the same type of test. So there were different tests and different data compiled in one review paper, which is fine. But of course, there may be some limitations from that. However, I mean, Helena actually asked impact loads. I mean, I would try to distinguish between impact and higher strain rates, because what happens with impact, very likely you get delaminations between different plies simultaneously. And then you have exactly these problems that I mentioned before with interacting delaminations in different plies, which is even more complex than just having a single one at different strain rates.
Oh.
Just as a comment.
John Allen, you want to respond to this one as well?
Yeah, exactly. Because what you see, impact is very difficult to analyze. You left with what happened afterwards, and you have to try and figure out what actually happened during the impact, right? I don't think I've seen anybody live record that. It would be cool to do, but I don't think we're there for testing technology. But if you look after an impact, what you see is kind of a staircase pattern. So between each ply where there's a fiber orientation change, there will be a delamination, typically bounded very strongly between the 2 fiber directions. If you have a quasi-isotropic layup, you have 45-degree wedges basically stepping through your material, and at the edge of each of those directions, there's a matrix crack connecting up to the ply, the interface above or the interface below. So is that a migration? Is that the matrix cracks happening first and then starting the delaminations? Is it just, should we talk about matrix cracks and delaminations, or is it just one 3-dimensional crack? For me, is a bit open questions. And a bit the same, even a delamination is a combination of fiber matrix disbonds and matrix cracks at the micro level, right? You have the fibers being disbonded, and then in between the 2 fibers, there's a small ridge of matrix that needs to be cracked through. And then we call that combination the delamination.
Yeah, and that also applies in the migration plane. The same
Exactly.
thing there.
Yeah.
Yes. Okay, I think we have largely addressed that one then. Then questions about size effects. Anybody want to comment on that? Michael, you're the size effects expert here.
I'm seeing the question. Let me find it.
Yeah, it's in the regular chat, not in the Q&A.
Okay.
It's basically, what about the values for size effects? Are there any size effects in the laminar?
I don't see the okay. I don't see the question, I'm afraid. But who's it from?
Shiva Gudam.
That doesn't appear in my Q&A. There must be a time delay or something because
it's in the regular chat, not in the Q&A.
I'm sorry, it's in the chat.
Yes.
So size effect on what? Well, I don't see it in the regular chat either. Oh, okay, yeah. Right. I see it. Right.
Okay.
These values for size effects. So I'm not quite sure what. I mean, what?
But I guess if you test a much wider specimen, some of these type of tests have been done for sure in setting up the standards. I guess also including for mixed mode bending, although I don't know specifically whether that happened.
So I think, well, one of the things depends how you define size effects. I think size effects in my book are more associated with strength rather than fracture. But I think a crucial one is the effect of specimen thickness, because especially in mode 1, I mean, maybe we were supposed to be talking about mode 3 and other ones, but in mode 1, fiber bridging is really strongly dependent on the stiffness, which depends on the thickness of the specimen. So I don't know whether that applies. I haven't really seen anybody look at that in mode 2 or 3. I don't know whether Emil or anybody else has seen that, but I suppose it brings us into the whole question about resistance curves as well, which again, unless we've got good methods for measuring them, it's very hard to determine resistance curves. Has anybody got anything on resistance curves in mode 2 and 3?
I mean, the difficulty with mode 2 is that the actual process zone is quite large compared to from mode 1, and so that process, and I think the R curve effect we see in the mode 1 test, I think, is an artifact of doing unidirectional specimens where you get fiber nesting. So if you decide to compact your specimen more during the manufacture, you end up with more fiber bridging and you get a higher toughness things. But I think it would be interesting to look at thin plies to see how this migration occurs. And I think, as Robin alluded to, it's a competition between the delamination process and the intralaminar fracture, the ply cracking process. So if you have a material that's very resistant to ply cracking, perhaps that will inhibit migration from occurring. I think that would be something interesting to look at from a modeling perspective. You need a model that would be able to capture both those intralaminar and interlaminar processes, but you could start to play around with those parameters to see how you could influence the overall damage growth.
We do see that with some of the tests that have been done on impact on thin ply laminates, that in some cases, instead of the sudden emergence of multiple delaminations connected by transverse cracks, you may just get a single delamination in the midplane, which doesn't form the traditional multiple delaminations because there are no matrix cracks to help it join up through the thickness.
Do you have some of those at Bristol?
No, that's a paper from Japan I remember seeing a few years ago.
I'd be interested to look at the fracture surfaces, because if it's not migrating, then it would be generating a high mode 3 fracture potentially. So that would be quite interesting to look at.
Yeah.
Any further comments on size effects?
Yeah, I think it also comes down a bit to this whole discussion about, is this a material property or not, right? So maybe just to show, we did recently some tests. Wait, I have to share it the other way. This is ELS tests with DIC from the top. So you can see the strain distribution across the top of the specimen. And this is also from Vinji's thesis. And he then processed it to an equivalent strain energy density And then the idea is that this gradient shows you where the crack front is. Right, so we can argue about the exact value of where we determine the crack front, but the main point is that this crack front is not straight. Which also suggests that if you make your specimen wider or narrower, then you have more or less influence of the edge effects, which would then influence whatever value you're trying to extract from this with the classical data reduction schemes, which do not take this into account. And what you also found, which is not necessarily a size effect, but is linked, is that in these planar tests, because you're clamping the specimen, you get in-plane stretching as you're deforming it out of plane. And so the extrinsic toughening is different than in your classical mode 2 tests. So if you get a mode 2 fracture toughness value from the classical tests and you plug that into a model and try to predict what will happen in the planar delamination growth tests, you will be off because the fracture toughness does not match what you would extract from the planar test. And I think there's a lot of tricky terminology here where we need to be careful, okay, what are we calling exactly and what is the right terms to be using? But I think the main idea is this is another effect that is, for me, the real question is if it's not a material property, is there value in doing these coupon level tests, at least from a design point of view? I mean, scientifically, we can learn from it. But yeah, if you get a number out of them, but that's not going to be applicable to real structure because the boundary conditions are different, then what are you doing with that number?
Could you just clarify these tests where you had a skewed crack front? How was the specimen? How did it look like? And what was the layup?
Yes, so it was the classical ELS test. Let me see if I have the picture here. And so there were the difference. So we did. I think
can you share your screen again, John?
Yeah, exactly. I was looking for the right picture to share. So here it is. So it's the classical CLS setup. And then you can see from the top, we monitored the specimen of DIC. So we had different specimens, but also ones with UD layup, so for the UD. And also there you see a little bit of a thumbnail shape. We also had some multi-directional specimens, and then of course you see a much stronger twisting of your crack front.
But that indicates some sort of asymmetry, I would say, yes, in the layup or in the test setup or something.
Yeah, but I think what has been analyzed, and it's common also for the DCB specimen, that you do see this kind of thumbnail shape, because at the edges of the specimen, due to edge effects, you get a little bit of closure, if I remember correctly. So typically in the center of the specimen, the crack always grows a little bit faster than at the edges. And of course, if you have asymmetries in your loading setup or in your layup, for sure, then that all gets exacerbated, and then all of these just get even worse. Also, another size effect is if you have a multi-directional layup. So we've done some tests of multi-directional layups. Then you get this kind of migration effect, and then you get a fiber bridging-like behavior. Again, we can argue about terminology, right? But you get that bundles of fibers get pulled out, but are still attached on either side. So in a 0-90, for example, you get this oscillatory migration, but it doesn't happen equally across the width. So you end up with these kind of crosswise bundles of fibers being pulled out and attaching to each side of the specimen. And these fiber bundles, of course, are only as wide as, or as long as your specimen is wide. So if you have a wider specimen, you can develop much longer bridging fiber bundles, which I expect would then give you very different toughness values if you don't correct for it somehow.
Okay, I would propose we move to the next question by Ali Shivaye Kojuri. I'm probably mispronouncing that, about VCCT and the fact that the self-similar crack propagation assumption is not valid if it migrates right away. Anybody care to comment on this one? I know John Allen has been working with VCCT.
Yeah, I mean, I think it's a very correct point, and for me, indeed, an open question. Right, so I think, well, even getting VCCT to work with a migration is already tricky, I would say. So I guess you have to kind of like predefine the migration already beforehand, and then So in the VCCT results I showed, that's why the migration was not included, right? So we're showing the situation just around the Teflon insert before any migration has happened. If you yourself define that crack path in and only then run the VCCT, sure, I guess a result will come out, and then we have to debate, okay, what does it actually mean? So yeah, so it's, I think, yeah, open question how to deal with this.
I agree. Anybody else wants to comment on that one?
Well, just a clarification about what we're talking about VCCT. Are we talking about what's in Abacus, for example, where you use the Abacus interface approach? Because you can, in principle, use a virtual crack closure, even if the crack is not self-similar. You just work out the energy balance from propagating a crack versus not propagating a crack. And that's not how it works in the Abacus, but in principle, I think you can calculate it.
Yeah, good points.
Yeah, I would like to say also something. I'm not sure I am understanding the question, because if you have a kink of an existing crack, then because to have the migration, you need first to kink from the original crack, my understanding. And then the first thing you have to do is to determine the direction of kinking. And there are several criteria for this. One is the maximum value of the hoop stress. Another is the maximum value of the capacity of releasing energy. In accordance with any of them, you establish a new direction of the crack, and then you can apply regularly your let's say, VCCT scheme. It should work. I have used this in many cases. For instance, when you have at another level, for instance, micromechanical level, one debond, and the debond stop when you have a pure mode 2 in between fiber and matrix, and then the debond kink and enter into the matrix. You can apply VCCT, no problem, in the new direction, obviously.
Okay. Now we move to the next question in the chat about linear elastic fracture mechanics that's used for determining the energy release rate, but its applicability is never checked. And given the large fracture process zone, is it valid? Anybody wants to comment on that?
I can say a little bit. I mean, the standard tests, I mean, for the mode 1 DCB, there are exact criteria that you have to check that will tell you whether LEFM is applicable or not. I'm not sure whether they're as explicitly stated in the mode 2 standards, but I mean, of course, I would agree that probably in practice, very few people do it, but the procedures are in place, and you have the tools that will allow you to check. Whether you do it or not is then your decision.
Yeah. Further responses to this question?
Yeah, I think it's a very fair point, especially in mode 2. Indeed, you see these large process zones, which I think in a lot of the data analysis, they kind of get folded into then working with an effective crack length. Yeah, we can try to model it more explicitly, but I think it's indeed a good question. Okay, how do we deal with these process zones? What are we calling a crack tip? What are we calling a crack length? And yeah, from that follows, okay, should we do something different or correct for it somehow from LEFM point of view? Because again, if your process zone is different between two setups, then yeah, probably you're going to find a different toughness value. Yeah.
Okay. I think that's then answered. Then we move to one in the Q&A section about the fact that the material property doesn't need to be a scalar. It could also be vectorial or tensorial in nature. I maybe want to first respond to that. In one of the first workshops we organized about strength, specifically tensile strength, we also had a quite elaborate discussion on whether, given that you have quite significant size effects in tensile strength, is that a material property? No, it's not. But you could also say you could capture the Weibel modulus and the Weibel scale parameter and design those two as the material parameters that determine the tensile strength. So that's not even vectorial or tensorial, that's just two parameters to characterize the material parameter we call longitudinal tensile strength. Now, yeah, maybe it's vectorial or tensorial. I think that's maybe an interesting way to look at it indeed. Emil?
Yeah, so I'm very much of agreement that when we started working on composites, we kind of assumed the fracture toughness was a material property, delamination resistance was a material property, and we're very comfortable with strength and stiffness being directional in composites, and there seemed to be a resistance to toughness, delamination toughness being a directional property, and I think it is. The cracks like to grow along the fibers, so that perhaps is the lowest toughness along the fibers. But I think my approach to this is to look at the fracture morphology, and if you have two fracture surfaces that have the same fracture morphology, then the toughness associated with that, which is what's generated those morphologies, is probably the same. So in the samples we looked at where we tested a 0-90 interface, if we looked at a delamination and a plus-minus interface where we'd grown along one of the fiber directions, the morphologies are the same. So I think you could use the fracture toughness along the fibers for a 0-90 to measure the fracture toughness in a plus-minus if you grow along one of the angle plies. So I think I'm very comfortable with it being directional. I think it's something that people need to recognize. And this is, again, coming back to the sort of isotropic perspective on composites. Composites are not isotropic. We have to live with that, I think.
Further remarks on this?
Yeah, I agree. So it's the remark I would make is that I was also comfortable with it being a directional property or tensorial property, what you want to call it. But the issue with calling it material property, as we currently measure it, is that we see a lot of these effects like fiber bridging or other extrinsic toughening. We see differences in process zones, and until we fully understand how to account for that, they can kind of work their way into the number that you're measuring. So you get a number out of the test, which is not the pure material property, but it also includes all these other effects that are not correctly accounted for. And yeah, so then the question is, what is really the material property, and is that a meaningful value if all these effects are otherwise always there?
Yeah, Federico?
Yes, I don't understand very well the beginning of the question, of the comment, because the stress tensor is not a property of a material. It's a characterization of the stress state. And you have many properties that are scalar. So we cannot invoke this character to say that fracture toughness is a property or not of the material. I think that we have agreed that independently of the assignment of mode 2 and 3 classics, if we assign the II and the III, these can be considered properties of the material, independently of the fact that they are not associated with the previous definition of mode 2 and 3. But it's not connected, in my opinion, with the necessity or not of having a property associated with a scalar or not.
Okay. Then I think there is our 7th panel member wants to show some data. Go ahead, Robin.
Are you talking to me?
Yeah, sorry.
I think I am not allowed actually to share data
yes.
because I'm not a panel member.
Wait, sorry, I will give you permission. Now you should be able to.
Yeah, okay. Let's see. I share and let's see, what do I share here? I share share what window? This one. Do you see this? It's a paper from 1996.
Yeah.
Yeah, I thought it was so. It's not about mode 3, which is our main topic, but I thought it was quite interesting. We did tests many years ago with buckling-induced delamination in specimens, and it turned out from the FE analysis that this delamination growth was actually, let's say, almost 90% mode 2 dominated. So it was more or less fully mode 2. And we looked at delamination growth in a 0-0 interface, in a 0-5 interface, and in a 0-0-90 interface. And the interesting thing is that in these tests, we get sort of stable delamination growth. And you can see that the values are very, very similar for all different interfaces. The difference was that for the 0-0 interface and 0-5 interface, you have a much higher initiation value. But actually, for the growth, they were all similar. Of course, this was a growth where the delamination plane was sort of trapped between surrounding 0-degree plies. So it still agrees with, the reasons of Emil that if you don't trap your delamination growth between 0-degree plies, then you get migration and then you don't get this kind of delamination growth. But I thought it was interesting that you can get stable values which are all much lower than the initiation values you see in a sort of conventional ENF test. So that, I think, indicates that the initiation values you get from, for example, a conventional ENF test is not very relevant for, say, predicting delamination growth in impact testing. The values you get, 600, 700, 800, they are far too high. And you should actually look at the values for this specific material around 500 joules per square meter. I think if it would be possible to do a mode 3 test, I think you may find similar things. But of course, in most cases, you will just get migration then.
Emil? You're muted.
Just to comment on the difference in fracture toughness between a 0-0 and a 0-90. I also was able to grow cracks at a 0-90 ply interface. Could I share my screen?
Yes, you should have the permission already.
Yeah, so what happens is, just put that in review mode. So in the 0-0, you get these shear cusps. If you move to a 0-90, you start to get these secondary, you can see the shear cusps, but you also get these secondary gouges, is what we call them. And they're associated with these secondary cracks that initiate at the 90 ply below that, and they extend and emerge at the delamination plane. So this is an added fracture mechanism, so it's adding to the toughness. So I actually found, under mixed mode conditions, I think it was about 40% improvement in the fracture toughness in the 0-90 as compared to the 0-0 for the same material system. But something you probably need to bear in mind with this is that if you have a 0-0 ply interface, the consolidation tends to promote nesting and you have a thinner interlaminar region. But if in a 0-90, nesting isn't encouraged, so you actually end up with a thicker resin layer at that interface, and that in itself would tend to enhance the toughness. So I think you have to be quite careful in comparing a 0-0 to a 0-90, for instance, because it's not just the ply direction that changes, but the actual architecture of that interface.
Follow-up remarks on this? No. Then I actually want to get back to something that we was mentioned by Emil at some point, that you suggested that some models might benefit from just imposing that the delamination should grow along the fibers. I actually question that, because essentially then you're imposing something into the model, which in principle, if you set it up correctly, it should be able to predict it by its own, right? If on the condition that you have the right input parameters and the right damage mechanisms activate, and those are maybe quite severe assumptions in this case, but the problem is then those assumptions, and I would rather work on that than imposing it in the model to override issues with the parameters.
Yeah, I mean, we were thinking delaminations grow along the fibers. Is it because the toughness along the fibers is lower than the toughness if you try and grow oblique to the fibers and then get the migration process? That was one approach we took. But so that could be one way. You basically define your toughness as having a direction whereby it's a minimum when you're along the fibers, and implant that into your FE model. I mean, I don't know how you would code that with a VCC or a cohesive zone model. I think the difficulty with the cohesive zone model is that you need to have some sort of directionality in that model. So that could be one approach to that, but we weren't entirely comfortable with that because we didn't know how, as you changed your angle, how much that toughness would increase. So the approach we took is that it will try and grow along the fibers, but as you become more and more oblique to the fibers, you reach a point where a migration process occurs. And then that is perhaps a criterion that you have to impose in your model, that if you're trying to grow a delamination at a particular angle to the fibers, the failure mechanism actually then changes to migration, and you migrate it to a new interface whereby it could then grow along the fibers. But I'm not a modeler, so I'm not quite sure how you would formulate a model that could capture that process.
Yeah, it's very challenging from a modeling point of view, but I think in principle all the tools are there to do it. We just don't have the right input parameters, and some of them, I would argue, cannot even be measured because it immediately migrates away, as we've been discussing quite extensively. But you do need to know what the fracture toughness is in some of those interfaces, which you can never measure. So it's a catch-22 problem that you have here. Federico.
Yes. If I think in the interface in between two layers as a plane, I have no reason to say that it's going to increase or decrease depending on the orientation of the fiber. So to think about the problem, I need to go to a different scale again. So if I think that Emil said the fundamental rule, delaminations preferably grow in the fiber direction. I agree with this, but there must be reasons from a micromechanical point of view to distinguish in between the advancement of the growth in the direction of the fiber and the advancement of the growth in the direction normal to the fiber. If this is the direction observed, then, for instance, one explanation is that the involvement of mode 1 at micromechanical level, which is the real mechanism of damage. At micromechanical level, the mode 1 is more involved in the direction, on the growth in the direction of the fiber than in the transverse direction. Because in the transverse direction, you have clearly mode 2. Mode 2 between fiber and matrix in the damage formed by the bonding, which implies that the right-hand side of the equation, the apparent value of the toughness will be bigger, and then there is a reason from a micromechanical level to do this. So I agree that it would be good to have a possibility to do it by the model itself, but then you need to model at micromechanical level and to put all the properties at the micromechanical level, which is not an easy task. But at the same time, I have to say that if we want to provide engineers that perform design to help in the design, probably not in the aeronautical industry, but for instance, designing a Formula 1 car, you need to, one key point is the capacity of absorption of energy in an impact. And this is controlled by this apparent value of G2C and G3C. If we had a fundamental background of the origin of the absorption of energy, knowing these values, we could help people to design laminates to absorb more energy during an impact. But this is a very complicated matter. Unfortunately, I'm very old and I have no time and energy to do this. But I was in the 30s, probably I would try this, because I see in this matter something that has a clear engineering application for a particular area, which is, for instance, Formula One car.
Yeah, I think, Robin, you want to respond to that, or you want to ask a new question?
Well, maybe add a new one. I mean, I think that if we for sure, if we want to be able to cope with migration, we need a sort of, we cannot just have a cohesive model. We need to have a model for matrix cracking, translaminar cracking as well. And it's a competition. And but I think the question is, if we have interlaminar growth, we need to have a model which predicts the toughness as a function of fiber angle. I mean, I think we cannot say that the crack has to grow exactly along the fibers, because we know that it can actually grow as a delamination in the plane, even if the fibers are not completely perpendicular to the crack front. So, but maybe, I mean, we could assume that it's just independent of the fiber angle, but I'm not completely sure that's a good assumption. I think there is an influence of the fiber angle as well. So we would like to be able to test that, of course. There have been some tests made on that. But another thing on this with impact, I mean, to use G2C to predict the delamination threshold, it's been extremely successful. To use the toughness is not difficult. It's actually very reliable to predict the delamination threshold load based on mode 2 toughness. So it's not more difficult than using mode 1 toughness, for example. And, you know, generally when you have an impact, it's a multi-directional laminates where fibers are in all sorts of directions to the impact direction. And we still can use it for all cases I have seen. So, but I mean, more generally, of course, we would like to have good models for both influence of fiber angle and also to combine them with these models for crack migration, which then requires actually I mean, generally we need a 3D model, or at least some sort of semi-3D model with thick plies models as using, you know, ply shell, thick ply shell elements at least. Otherwise, we cannot predict migrations.
Yeah. Anybody want to respond to that?
Yes, just a comment. I agree that it is the same level of difficulty when using G1C or G2C to predict the behavior of a structure. What I was trying to say is that to optimize a value of G2C or G3C as a function of the high number of events that affect these final values, like for instance the stacking sequence, the thickness of each lamina, the orientation, and of course the properties of the fiber, the metrics, and the interfacial properties, is much more complicated for G2C than for G1C. That's all. But of course, having the value is the same difficulty. I agree with you.
Are there any further questions from either the attendees or the panel members? I maybe have one more for Emil related to this angle that you identify in the shear cusps. I think you had it somewhere on your, well, essentially already on your first slide where you show this angle in the shear cusps. Are you? Yeah, you can share it again if you want. It's
Yeah, sure.
Easy for the attendees. Just because you say the imprint angle depends on the mode mixity, and you could imply from that you can use this to measure the mode mixity, but do you want to go that far to use it as a quantitative measure of the mode mixity? Because I don't really see how you can easily identify a precise angle from those shear cusps.
Yeah, that was the principal focus of my PhD, is to measure that angle and infer the mode mixity. The idea is that if you're presented with a delamination surface, you could characterize the cusp tilt angle, and they all tilt at the same angle. But it just proved to be very difficult to do that. Just, this was in the mid-90s, so very difficult to do that. But I think maybe with AI, you could look at a fracture surface and you could actually make that measurement and actually use AI to characterize the imprint angle. So it's not the angle. Let me put this on full screen. It's not the angle of the it's not the angle of the cusp itself, because that undergoes sort of plastic deformation as it shears. It's the imprint that is the fracture that's being formed. So under pure shear, that should be at 45 degrees, of course. And so the idea here is that maybe we could look at fracture surfaces and interpret the mode mixity, and then use that to validate, predictive models. That was the thought behind that. And then similarly with the mode 2-3, you have this rotation of the cusp. So if I go to that final slide.
That was going to be my follow-up question, because there it may be a bit easier to do.
Potentially, yeah. I mean, what was encouraging is that you can see they all seem to be reproducing a similar angle. And potentially you could look at making a measurement of that angle. I've indicated it here. And then use that to interpret what is the local 2-3 condition. But I think with the advent with image analysis tools and AI, maybe you could basically characterize a whole fracture surface, put it through the AI, and actually get a map of what is the mode 1-2-3 mixity of the fracture surface, which I think would be very useful both for failure analysis of crash investigation, but also model development things.
Yeah,
that angle is quite small. You're saying G3 similar to G2. The angle is actually quite small.
It's kind of, I think, because you get the migration process occurring. These first two images were from that standard test that we developed, the width tapered ELS. And so if we tried to go more than this, we got a migration occurring. This final image here is actually from a fractured component that I looked at, and this I'm interpreting as a mode 3 dominated fracture surface, but I've not been able to characterize that in a standard test because it always migrates. So I think there still is some work to be done on trying to understand how you could actually develop a test where you inhibit the migration process and allow you to generate a delamination under mode 3.
Yeah, interesting answer indeed. Are there any further questions? I don't see any more from the audience. We could also gradually start wrapping up if we run out of things to discuss. Maybe anybody wants to make a final remark on the state of affairs in mixed mode and mode 3. It's very complicated.
And maybe a question in a general sense. I mean, do you have any ideas in which direction a mode 3 test would have to be developed?
That's a good one.
I mean, I must say my conclusion from this is I'm beginning to wonder whether it's worth it, because really mode 3 seems to be rather artificial, and is it really worth chasing it down? I think we perhaps relied too much on the conventional isotropic fracture mechanics and thinking of it in the way that we did for metals. Maybe that's not really the way to do it for composites.
I would be inclined to agree with that. I think maybe that effort is better spent on trying to predict the migration properly, which means you would have to look at intralaminar fracture toughness, which we also very rarely do. How do you incorporate that into models? There's a lot of challenges that I think are probably more important than characterizing it in mode 3.
I believe it's a little bit unfortunate that James Radcliffe couldn't attend.
Yeah. Yes.
He may have a different opinion. I mean, I think he was one of the people who brought the mode 3 tests back after, the initial round robin was something in the early 1990s, and then there was no activity whatsoever on mode 3. And he brought it back to some extent. But I think recently has not been much activity, and it's probably just the complexity and difficulty of developing a proper test that works.
Yeah. Robin?
Yeah, just two things. First of all, I wrote in the chat originally that I missed a reference to Rod Martin's sort of critical analysis of the SCB test. Is as important as Radcliffe's analysis of the ECT tests. And both those analyses basically show that the tests are imperfect. And I would say that the SCB test is much more imperfect. It's extremely non-uniform G distribution and a high, actually the mode 2 component was many times higher than the mode 3 component at certain parts of the crack front. So we don't have a good mode 2 test, 3 test, but I think it's work on that should continue, but it's not a thing for industry and for designers, as it's something for PhD students and their PhD supervisors to sort of try to develop this maybe impossible, but perfect mode 3 test. It's so far, I think that we have better assume that G3C is equal to G2C. And then, of course, we have also to consider migration criteria. But this is the best we can do for the moment, because we cannot compare when we don't have a good test.
I agree with the comment. I'm fully aware of Rob Martin's paper on SCB, and I think initially I even tried to reference it in my slides, but then considering the short time I had for presentation, I focused more on the ECT, because I thought, this looked maybe more, there were better perspectives for that than for the SCB. And maybe I should have cited that, and or at least noted it quickly in the presentation. Sorry for that, but I was aware of that, and but it was just kind of due to time constraints that I didn't explicitly mention it.
Federico?
Yes. I started saying that the values that we are getting from the test associated with G2 and G3 didn't satisfy the three conditions we, Michael, Yentl, and me, we put for a figure to be considered a material property. But if the question is if fracture mechanics is applicable to composites, definitely my answer is of course. Yes, but at different level. For instance, to learn about the mechanisms of damage that happen typically at micromechanical level, everything associated with fracture mechanics is absolutely applicable. No question about this. Well, in fact, most of the time we need to apply interfacial fracture mechanics, which is much more complicated than typical fracture mechanics in an isotropic material. So, but I have learned a lot. I have understood many problems using fracture mechanics at this level, like for instance, the in situ concept of strength. Consequently, we need to continue applying fracture mechanics to understand many phenomena associated with damaging composite. Another question is the representativity of translating directly fracture mechanic concepts to composite at meso or macro mechanical level. So in most of the cases, I think that the value, I mean, the concept is applicable, the value is not applicable as a material property.
Yeah, one important thing, I think, important work was by Shia and Hutchinson in quite many years ago. They demonstrated there how actually shear hackles, these sigmoidal cracks, how they can be linked to mode 2 toughness and G1C. And they established a very good relation, which agrees with most experiments on of course, there are sort of deviations, but basically 3.1 times G1C for D2C. That applies as long as you get the sigmoidal cracks, you get shear hackles, which applies for brittle and semi-brittle materials. Emil had a PhD student looking at this for sandwich panels, for example. But if you have a very tough matrix, like more behaves like butter when you use your knife, it doesn't matter if you spread out the butter or if you cut through the butter, you consume the same plastic energy. So for very, very tough resins, G1C and G2C approach each other. So I think you have to realize that all is linked to what happens at the sort of micro level in terms of failure mechanisms. But take a look at that paper by Shia and Hutchinson. It's really interesting, and it agrees with what you see in microscopy and so on. They looked at this, tunneling, and it's actually mode 1 cracks which are tunneling, but they are sort of tunneling in an inclined angle.
Emil?
Yeah, I mean, it's quite a simplistic approach to it, because treats it as a 2D problem. What actually happens is the cracks initiate at the fibers. Those cusps form from the fibers and spread into the matrix region in between, and then form the sigmoidal cracks. But it's just treating mode 1 and mode 2 as the sort of same process is not really a valid approach, because as I mentioned earlier, if you start to degrade the fiber matrix interface, you improve mode 1 toughness, but you reduce mode 2 fracture toughness. So I think it's too simplistic to just say mode 2 is mode 1 at an angle. I think there's a lot more to it than that.
Okay, I think that's probably enough concluding remarks. Maybe just to conclude fully, just a reminder that somewhere in the future we'll have a workshop on interlaminar fatigue and eventually one on translaminar crack propagation. So if you think you have something interesting to offer, to present, you can always get in touch with me, Mike, or Federico, and we'll decide whether it fits well enough with the topic of the workshop. And with that, I would like to thank you for your attention. For following the workshop. It was a pleasure to moderate this, and I hope to see you again at one of these future workshops. Thank you all for joining.
Thank you.
Thank you. Bye.
Thank you very
Thank
much
you.
for the organization.
Bye.
Okay. Goodbye.